Here I have a structure of hexane. So notice that there are 6 carbons, hence hexane. They're all connected by single bonds. Now, notice that I can move this molecule around. I can look at it from different angles. This is very much a 3D structure. I know on a page, we draw it as these little zigzag lines, but this is what it actually looks like. And note the tetrahedral geometry of each carbon in this molecule. Another thing you will notice is that all of these single bonds can rotate. So I can rotate these at room temperature in different directions. And this is happening constantly if a molecule is at room temperature. All of these bonds can rotate, which means that this molecule can take on different types of conformations. So typically we draw it in that straight chain zigzag line structure, but notice how here it has this really weird bent shape. And there are lots and lots of different ways that you can rotate these bonds. So it's going to be really important to recognize when you are drawing a structure from a different conformation and when you are drawing a completely different type of molecule. So we're going to learn some tools that will help us distinguish between different types of molecules and different conformations. As we saw, single bonds rotate. So at room temperature, really at any temperature where atoms can move around, all of these bonds are going to be rotating constantly, which means that they can take on what we call different conformations. So a conformation is really a representation of the way that the bonds are aligned. So the representation of the 3D structure of a molecule. And it's really answering the question of how are these bonds oriented? And as you saw when we rotated all of those bonds, these molecules can take on lots of different types of conformations. So it's going to be really important to recognize when you're looking at the same molecule in different forms of conformations. So what you're going to do is find the longest continuous carbon chain and number it. So I'm going to go here, I'm going to count the number of carbons. I see that there are 6 carbons connected all together. Then if I look at the next structure, there are also 6 carbons that are connected together. And same on this structure. And also on this structure. So all of these have 6 carbons that are connected to each other in the same pattern. So in all of these cases, we're looking at hexane. It has 6 carbons, all connected by single bonds, and they're all connected in that same pattern of 1 connects to 2, 2 connects to 3, 3 connects to 4, and so on. So we would say these are all conformations of the same molecule, which means all of these represent hexane. I know they look a little bit different because they're rotating, but they're all hexane. And you can see the same sort of thing happen in condensed structures or expanded structures. So if I look down at the different condensed structural formulas, notice that in this one, I have 6 carbons all connected together in a chain. And same sort of thing on the next structure. This connects 6 carbons to each other. On this next one, I have 6 carbons connected to each other in the same pattern. And also on this one. So these are also all conformations of the same molecule, and these are all different representations of hexane because all of these bonds can rotate around. So just be really careful. Don't let that trick you. I know the molecule can look in different, it can appear in different ways. There can be different bond angles. Well, bond angles won't change much, but you can see that the bonds can rotate and they can look quite a bit different, but they're all the same. So go through, find the longest continuous carbon chain, number it, and see, do they all connect in the same pattern? So I'll show you an example where they aren't the same structural formula. So let's look at a conformation versus what we call a constitutional or structural isomer. So in conformations, we said these are just different representations of the same structure. So for example, I could draw up hexane in this form, or I could draw hexane in this form. And these are the exact same thing because they have the same connectivity. So if you have different conformations of the same molecule, you have the same molecular formula, and the same atom connectivity. So in both of these cases, we are looking at hexane. When we're looking at structural or constitutional isomers, these are synonyms, so two words for the same thing. We are looking at the same molecular formula, but different atom connectivity. For example, let's say we are looking at C6H12. This is the molecular formula of hexane, so just the molecule we were just taking a look at. I could draw hexane like this, which is what we've been doing thus far, where all of these carbons are connected together in a straight chain. But I could also draw something like this. And here I still have 6 carbons and I still have 12 hydrogens. And if you're not sure about that, I encourage you to expand these structures out into the expanded structural formula so that you can prove to yourself that these have 12 hydrogens, both of them. But notice that here atom connectivity is different. So I have, in the previous example, all 6 carbons were connected together in a straight chain. Here I have, the longest chain I have is 5 carbons. And then there's 1 carbon here that is really serving as a branch. So this is a branching type of structure. These molecules are different. They have the same molecular formula, but they are different molecules with different properties. These are what we call structural isomers or constitutional isomers. And we can continue that. So one molecular formula can have lots of different types of structural isomers. Notice that this is also C6H12, but in this case, there are 4 carbons that are connecting together in a straight chain, and there are 2 branches. And the larger that molecules get, the more structural isomers they will have. So by the time you get to decane, when we're looking at C10H22, this can have 75 structural isomers. And when you get larger, we can look at hundreds upon hundreds of different structural isomers. And that's why it's so important for us to be able to draw the structures and what these molecules actually look like. Because at this point, these molecular formulas are no longer going to cut it. It's just not enough information to be able to distinguish between these molecules. So let's take a look at how are we going to draw different structural isomers of a chemical formula. And I'm going to start this off in a relatively simple way. I'm going to say, let's take C4H10. So that's our molecular formula. And it's going to be really important to distinguish between the different definitions. So make sure you know what a molecular formula is, what expanded, condensed, and line angle means. I think it's simplest to do this in a line angle format. It'll just make your life easier. And the process will be, the first thing we will do is start with a straight chain alkane. So I'm going to connect all of these carbons to each other in a straight chain, just like I've been doing thus far. So I'm going to draw this. There are my 4 carbons all connected together. Then I am going to shorten the chain by 1 carbon. And attach it somewhere else. So if I were to take this structure right now I have 4 carbons connected together. I can take this carbon, detach it, so basically pluck off the entire thing, and instead of connecting it to carbon 3, I can connect it to carbon 2. So I'm going to do that. Now if I pluck off that carbon 4, that goes away. I have 3 carbons connected to each other, and I'm just going to pop it on over here. And there's my structural isomer. Notice they have the same number of carbons. If you expand it out, you will see that they have the same number of hydrogens. They have the same molecular formula, but they are different molecules. This one has 4 carbons connected in the longest chain. This one has 3. So that's going to be the process. And the key here is just being careful to recognize when you are generating the same molecule in a different conformation, or when you are generating a different molecule. So let's do this in a slightly more complex example so you can see where you can kind of run into trouble. So I am going to do this with C5H12. Oh, one thing I forgot to mention. Notice this molecule is butane. This molecule is actually going to have a different name because it's a completely different molecule with different properties. And we will get to that eventually. We're going to name these in a very systematic way. And once you know how to name them, it'll be much easier to recognize whether you're looking at a different conformation of the same molecule or a completely different molecule. But we'll get to that eventually. Okay, so let's try this with C5H12. I'm going to start by drawing a straight chain alkane. Ooh, I think I added too many carbons here. Okay, there we go. So 1, 2, 3, 4, 5 carbons. Next thing I'm going to do is I'm going to shorten that chain by 1 carbon. So I'm going to take carbon 5 and I'm going to attach it somewhere else. So here it was attached to carbon 4. I'm going to attach it to carbon 3. And let's see what happens with that. Okay, so 1, 2, 3, 4, and I'm going to put a carbon on carbon 3. Notice these are different structural isomers. Now, what if instead of attaching that carbon 5 to carbon 3, I had attached it to carbon 2 instead? Let's take a look at that. Okay, so I would get a molecule that looks like this. And here we have to be careful because notice if I number it in this direction, I have the same atom connectivity as the molecule on the left. And here I'm numbering arbitrarily because we're not naming these. Once we actually start naming the molecules, we're going to have to be careful how we number the carbons. There's going to be a very specific systematic way of doing it. But notice this is actually the same atom connectivity. So these are the same molecule because same atom connectivity. So my rule number 3 would be recognize if you're generating the same molecule. And for now, you will do that by numbering atoms. We will have a better way once we learn how to name them. So these are the same molecules. So I would say these two are structural isomers. I'm gonna get rid of this one because that's just a repeat of the same molecule we've seen before. And basically you're gonna keep doing this until you run out of connections. So repeat until you run out of new connections. And there are no new molecules. All right, let's keep going. So I will tell you that this molecule or this molecular formula has 3 distinct structural isomers. So let's find the next one. Okay, I'm gonna take my 4-carbon chain and I'm gonna say, okay, well, what if I shorten that by another carbon? So let's try that. I am going to make this 3 carbons long. And if I were to leave this carbon on carbon 3 and move carbon 4 somewhere else, I'm just going to end up generating the same molecule again, just in a different conformation. So I'm going to redo this. I'm going to say I'm going to take a 3-carbon chain, and then I'm going to attach these carbons 4 and what would be carbon 5 to a different carbon. Notice I'm putting it on carbon 2 because if I put them on carbon 1, I'm just extending the chain in the other direction and generating the same thing. So I'm going to take both of these, I'm going to attach them to carbon 2. And that gives me the final structural isomer because this is a completely different connectivity. So the structural isomers that we made of C5H12, there were 3 unique ones. The first one was the straight chain 5-carbon or pentane. The second one was, it had 4 carbons in its longest chain. We don't know how to name that yet, but we'll get there. And the third structural isomer had 3 carbons as the longest chain. Now, a question that frequently comes up is, well, is there some sort of formula in predicting on how many structural isomers there are? Unfortunately, there isn't, and the larger the molecular formula gets, the more unwieldy this gets. Now, when I write problems, I always tell students, this is how many structural isomers I want you to draw, so you would know what you need to do. All right, that is a problem.